Okay, let's talk about exact equations. Now, to really appreciate exact equations from differential equations, it would be helpful if you had some multivariable calculus knowledge. The multivariable calculus knowledge that you would need, let's take a look at a surface here. So I've got a surface. The equation of it is x squared minus 2y squared is equal to z. So what we've got then is a height above a certain xy point given by that function. There's two independent variables, x and y, and they get plugged into that function, x squared minus 2y squared, and out comes a height. And that gives you this sort of a, that gives you this surface. The program that you're seeing here, this is dpgraph. You can go to dpgraph.com and download this program. You can draw this yourself. Now, before we start to worry about, I don't have multivariable calculus, if you don't have a multivariable calculus background, that's fine. You can still learn this section. It's just that those of you with a multivariable calculus background will so much more deeply appreciate what's going on here. That's all. And even if you don't, or you haven't taken multivariable calculus, the type of multivariable or the pieces for multivariable that I need are partial derivatives, which just means differentiating a multivariable function with respect to one of the variables. Let's say differentiating that x squared minus 2y squared with respect to y, keeping the x constant, or taking the derivative with respect to x and keeping the y constant. And also plotting multivariable functions, where the y then and the x are the input variables, the independent variables, and the output variable is the z, the height. Anyway, let's take a look. If I take a look at this surface, then I've got it plotted for I guess the x's go from -3 to +3 for the plot that I made, and the y's go from -3 to +3, and the z. So I'm in like a 6 by 6 by 6 cube. If I take a slice of this curve, a level curve, so I'm going to open up here, and instead of showing all of the z's from -3 to +3, I'm just going to take a slice at 1. So I've essentially set z equal to 1. I've taken a slice, a level curve. Now when I do that, I've implicitly defined a curve. This is the curve x squared minus 2y squared equals 1. It's an implicitly defined curve. Now, if I set z equal to 1 and take that level curve slice, now I have a 2D function. I'm not letting z change. Z, if you're not keen on the Queen's English, is set as a constant. So here's an implicitly defined curve. So here's our z is equal to x squared minus 2y squared. If I set z equal to 1, now I've got this implicitly defined curve. Let's differentiate this implicitly defined curve. So now, if I'm moving on this curve, now I can think of y as a function of x. If I plug in x equal to, I don't know, -2, I get out these two possible values of y. So at this point then, I can think of y as an implicit function of x. So I'm going to differentiate this curve with implicit differentiation. So the derivative of 1 is 0, the derivative of x squared is my 2x, and now I'm differentiating 2y squared, so I get minus 4y then times y prime for implicit differentiation. And instead of writing y prime, let's write it as dy dx. If I write it like that, then I can take this equation and multiply the whole thing by dx. So now I've got this equation where I've got some function times dx and some function, I'm going to go plus, some function times dy is equal to 0. This is the stage where if we started an implicit, or if we started an exact equation, that our problem would begin. We would be given something in this form and asked to solve it. Solve it? What do you mean? I mean find the equation such that when I differentiated it implicitly and multiplied through by the dx, that I would get the question again. So, exact equations start off as a function, a multivariable function set equal to a constant. That means that really what we've got defined in this case, f of x, y, equals a constant. That's our level curve, our slice. If we differentiate that level curve slice implicitly, thinking that y is a function of x because we're moving along some curve now, not a surface, then we'll have something that looks like the function differentiated with respect to x times dx plus the function differentiated with respect to y times dy is equal to 0. That's actually what we have. Differentiate this function with respect to x. You get 2x. There's that 2x. Differentiate this function with respect to y, treating x as a constant. There's the derivative with respect to y. So that's what we're getting here. The unknown function differentiated with respect to x times dx. The unknown function differentiated with respect to y times dy is equal to 0. It's equal to 0 because that's the derivative of the constant, the level curve slice that we took. So this is the form that implicit differentiation questions start with. We have to solve. What does that mean? We're given a question like this and we're trying to find what's the f of xy that fits into our particular problem. So in our case, we would have started like that. So this 2x, that must be the derivative of the function with respect to x. This minus 4y, that must be the derivative of the unknown function with respect to y. So in other words, that is the derivative with respect to x. If that's the case, oh, and note the funny d's. The funny d's are there because I'm differentiating with respect to x, but there's also a y variable. It's a partial derivative. We put the funny d's in there to tell you that they're partial derivatives as opposed to regular derivatives. But I can treat them, I mean, the differentiating rules that we learned in calculus all still apply. If I'm differentiating with respect to x, all the other variables are constants. If I'm differentiating with respect to y, then all the other variables are constants. So I can integrate this back. If I integrate both sides, I would get x squared is equal to f. There, I just integrated both sides of this equation with respect to x. Of course, there should be a plus constant here, a constant. But that constant could be a number like 12, and then when you differentiated it disappeared. Or it could be a function, right? I mean, it could be 12y, and when you differentiated x squared plus 12y with respect to x, the 12y disappeared. I don't know. So I can't just put a constant. I have to put, it must be equal to some function of y, and I don't know what it is. So now I know the unknown function. Well, I know everything about the unknown function except I don't know what this g of y is. But if I were to differentiate this equation with respect to y, I would get, well, okay, the derivative of x squared with respect to y is 0. The derivative of g with respect to y would be g prime, and that should be equal to the derivative of f with respect to y, which is that, which we're saying is this minus 4y. Well, now I've got g prime is equal to minus 4y. G prime, I guess in this case, let's replace that g prime, be a bit more specific. It's the derivative it's the derivative of g with respect to y. So if the derivative of g with respect to y is minus 4y, then g must be equal to minus 2y squared. I just integrated both sides with respect to y. Notice, didn't use the funny d's here because g is only a function of y. If I'm differentiating g with respect to y, that's its only variable. So, back up to this stage. I was done at this stage. I knew what f was, except I didn't know what the g was. Now I know what the g is. So, I can take that, and instead of writing g, I can write the thing that I know g is, and this is supposed to equal to a constant. How do I figure out what the constant is? Well, I need a point on the curve. You need to tell me where the level slice was taken. Again, I'm doing all this without all of the math from here downward. We don't really use multivariable. We do have a partial derivative in there, but I'm not thinking of it as a surface. I'm thinking of it as an implicitly defined curve, the level curve of the surface, a slice of the surface. So say that someone tells me that the point 1, 2 is on the graph, is on the curve. Well, then I can make my x equal to 1 and my y equal to 2 to figure out what k is. So that's going to be 1 squared is 1, minus 8, so k must be minus 7. So the solution to my exact differential equation is x squared minus 2y squared is equal to minus 7, let's say. Now, that 2, 1, that's not on the slice that I originally showed you. We made this slice by setting the z value, setting the height equal to 7. So what kind of point would I plug in here to get, we said that our slice was z equal to 1, not 7. So I would need to plug a point in here such that I would get 1. So if I want this to be equal to 1, then I'll plug in the point, let's say 1, 0 is on the curve, and now I'll get k equal to 1. So the k is the constant. The k changes with respect to whatever height you took the slice at. That is, in a nutshell then, an overview of what we'll be doing when we solve for an exact equation. Now, we sort of already knew the answer here because we started with the answer and made our problem, made our question. Let's start with a question that we don't know. So, if I see a homework question, that is supposed to be solved as an exact equation, we would have some function of x and y, m in this case, times dx, plus some function of x and y, n, as in this case, times dy is equal to 0. So this is the function differentiated with respect to x, the unknown function f. The n is the unknown function f differentiated with respect to y. I know that the m has been differentiated with respect to x because it's got a dx stuck on it. I know the n has been differentiated with respect to y because it has a dy stuck on it. Of course, not everything that's written in this form is an exact equation. How can I tell whether this is an exact equation or not? I mean, you just can't write any old bunch of x's and y's times dx plus any old bunches of x and y times dy, and it's an exact equation. Sometimes you'll do that and there won't be an overall f function such that when I differentiate it I get the m bracket, and with respect to x I get the m bracket, and when I differentiate it with respect to y I get the n bracket. How can I check? Well, remember Clairaut's theorem? Those of you with multivariable calculus will nod knowingly. No, maybe not. I remember when I first learned Clairaut's theorem, I remember the consequence of Clairaut's theorem, but I forgot the actual name of Clairaut's theorem. The idea is this. If I take the derivative of a function with respect to x and then with respect to y, I get the exact same thing as if I differentiate with respect to y and then with respect to x. In other words, the heterogeneous second-order partial derivatives are equivalent. So if you differentiate with respect to x first and then y, it's the same thing as if you differentiate with respect to y first and then x. That only works if the function is continuous, if there's a f to find. So that's your first thing, is you check to see if an equation, if I have an equation in this form, is it exact? I take the m has already been differentiated with respect to x. I know that because there's a dx there, and I differentiate it with respect to y. I take the n has already been differentiated with respect to y, and I differentiate it with respect to x. If I get the same thing, if they're equal, then the equation's an exact differential equation, and so the method that we're going to follow through will solve it, will work, but I have to check first. So, here's a problem. I've got a bracket times dx and a bracket with x's and y times dy equals 0. It looks like it's of the form, but the first thing I need to do then is check and see if it's exact. To check if it's exact, I have to take the bracket that's been differentiated with respect to x, and I need to differentiate that with respect to y. So I need to differentiate this with respect to y. It's already been differentiated with respect to x. When I do that, I get, now I'm differentiating with respect to x, no, I'm differentiating with respect to y, x is a constant. So I get 4xy plus 2 plus 0 when I differentiate this bracket with respect to y. Take the second bracket. Now the second bracket has already been differentiated with respect to y, that's why there's a dy on it, and I'm going to differentiate that second bracket with respect to x. And in that case, I get 4xy plus 2 plus 0. They're equal. So now I say Clairaut's theorem, and I know this is an exact equation. Now I can start. So therefore, it's exact. So now I can start actually solving the question. So then what do? Well, we go through the same procedure then. I know that this first bracket was differentiated with respect to x. So I'm going to integrate it with respect to x. I'm going to undo the differentiating. So I'm integrating that with respect to x, treating y as a constant. So I get the x squared y squared when I integrate the first piece with respect to x, plus, well, 2y is a constant with respect to x, so it integrates just to be that constant times x. The same thing as the minus 2x. And now there should be a plus c here, a constant if I was doing regular integration, but it's not a c, it's a function of y, because it's a constant with respect to x, but there could be y's in it. So this is the function, the unknown function. So I know the answer, except for I don't know what the g is. So I take this piece and differentiate it with respect to y. So I'm differentiating it with respect to y. Oh, minus 2x, that doesn't have any y's in it at all, so that disappears. So I took that, differentiated with respect to y, so now that's g prime of y, and this should be equal to then the second bracket, the function differentiated with respect to y, the unknown f function. So now, well, there's 2x squared y, 2x squared y, 2x, 2x. It looks like the g prime, the piece I didn't know, must be equal to 1, so the g, integrate both sides, is just equal to y. Integrate both sides with respect to y. So at this stage, I knew everything except for I didn't know what the g is. Now I know the g is y. So I'm just going to take this piece and replace it. And of course, it's a level curve slice, so it's not just equal to f, it's equal to k. So our plan for integrating, for solving, our plan for solving exact differential equations are: step one, check to see if it's an exact equation. So take the piece with the dx that's already been differentiated with respect to x and differentiate it with respect to y. Take the piece with the dy, it's already been differentiated with respect to y, and differentiate that with respect to x. See if you get the same thing. If you do, then Clairaut's theorem promises you that there is a function, an f of xy, out there to find, and you can do the procedure. What's the procedure? Well, first you take the bracket that's been differentiated with respect to x, and you would integrate it with respect to x. And of course, if you integrate, you go plus c plus a constant, but that constant isn't a constant with just constants in it. It's a constant with respect to x. There could be y's in it. So we integrate and we have like a g of y there. To find that g of y, we take the piece, to find that g of y, we differentiate our function. That'll give us our g prime of y. Could we set the whole thing equal to n, the piece that's been differentiated with respect to y, and then figure out what the g prime of y is, integrate with respect to y. Then we've got the two pieces. Make sure it's equal to a constant. How do I figure out the constant? Initial condition, plug in and get the equals k. A caution, that equals k part, in my experience, that's where people make mistakes. I see them do everything correctly, and then they've got equals f of xy or equals f, and then they find a constant. There is no f of xy in the end when we're solving an exact equation. It's equal to a constant, because you've taken a level curve slice. Even though exact equations come about by slicing 3D functions, by the time we see them in differential equations class, it's not a 3D function anymore. It's a 2D function, an implicitly defined 2D function with a slice at k. We set the height equal to k. Anyway, let's take a look at another example. So, we look at this example. Is it exact? Well, okay, I got to take the bracket that's differentiated with respect to x, this bracket, and I need to differentiate it with respect to y to see if Clairaut's theorem holds. So when I differentiate that with respect to y, I got to do product rule on the x cos xy. So derivative of the first, leave the second alone, plus leave the first alone, times the derivative of the second. So that's going to be chain rule for the cos xy. Remember, I'm differentiating with respect to y. So that's going to be minus xy sine xy. So all of this is just the derivative of y cos xy with respect to y. And the derivative of minus 14x with respect to y is 0. Next, I need to take the function that's been differentiated with respect to x, with respect to y, because it has the dy on it, and differentiate it with respect to x and see that I get the same thing. Again, product rule with this piece, derivative of the x with respect to x is 1, leave the second alone. The derivative of cos xy would be minus sine xy times the derivative of what's inside. Long story short, I get the same thing. The derivative of y with respect to x is 0. So by Clairaut's theorem, there is a function to find. There is an fxy. Therefore, it's exact. I would even put that on quizzes and tests and stuff in your notes. So you're telling the reader of the notes, the reader, that you've checked to see it's exact, and now you can proceed ahead with the method. What's the method? Take the piece that's been differentiated with respect to x and put it back, undo it, integrate it. So I'm integrating with respect to x. Oh, sometimes people, I'm integrating with respect to x. Sometimes people would ask me then, could you do this, could you take this second bracket, integrate it with respect to y, like start with the y variable? Yeah, you could, but it's arbitrary, so tradition says pick the x bracket first. Then there's a constant that has y's in it, a constant with respect to x. I'm going to take this piece that I'm going to take this piece that I differentiate, or that I integrated with respect to y. This is then equal to this unknown function, and I'm going to differentiate it with respect to y. So that's going to give me x cos, differentiate with respect to y, differentiate with respect to y, differentiate with respect to y, and this would be equal to the second bracket. All right, well, that tells me that g prime must be equal to minus y, because the x cos xy cancels out on both sides. So that means that the g must be equal to, I'm integrating both sides with respect to y, minus y squared over 2. So at this stage, I knew everything, except for I didn't know what g was. This is where I am. So now I can replace the g with what I know it is. And I'm taking a level curve slice, so it's equal to k. We're not given any initial conditions, so I can't figure out the k. I'm done. If I want to check, if I differentiate this with respect to x, I'll get the first bracket. If I differentiate this with respect to y, I'll get the second bracket. That's how I can check to make sure that I'm right. All right, some other ideas. If I take this first example, let's go back and get the first example. We already solved this. It was exact, we checked, but if I take that first example and multiply through by x squared, so I'm multiplying through by x squared, everything by x squared. So that's going to be x times x squared times x squared, x squared. I'm multiplying everything by x squared. So here's my original problem. I multiplied through, so it's solvable. We solved this. We've got the solution of it. There's the solution. There's right. There's, go away. There's the solution to this exact differential equation. If I took that and multiplied through everything by x squared, 0 times x squared, it's still the same problem. But now, is it still exact? No. And I'll leave this up to you to do. Differentiate this bracket with respect to y, differentiate this bracket with respect to x. You don't get the same thing anymore. You should check. So it's not exact. So if I can take an exact equation and mess it up by multiplying through by a constant, can I take an equation like this next one that's not exact and fix it? So let's check to see if it's exact. Well, I have to take the first bracket and differentiate it. I'm checking Clairaut's theorem, and differentiate it with respect to y. It's already been differentiated with respect to x. That's why there's a dx there. And when I do that, I get differentiate. I just get 2. If I take the second bracket and differentiate it with respect to x, I get, well, not 2. So they're not equal. So it's not an exact equation. So we can't proceed. But my point now is, if I take a look at this original differential equation, and before I check to see if it's exact, okay, consider that I could take an example and mess it up by multiplying through by an integrating factor. How about I take an example that's not exact, and we check to see that that was not exact, and then multiply everything through by the factor xy squared. So it's the same equation, just multiplied through by xy squared by that factor. Now I can see that it is exact. If I differentiate the first bracket, the dx bracket, if I differentiate that with respect to y, I get 6 xy squared minus, differentiating with respect to x, y x squared y, which is the same thing as if I differentiate the dy bracket with respect to x. So now, by Clairaut's theorem, there is a solution. My method, with respect to x, my method of taking the first bracket, integrating with respect to x, putting a constant g of y, then differentiating with respect to y, then making that equal to the second bracket, figuring out what g prime of y is, figuring out what g is, my method will work then. So what's the point? My point is that sometimes I can have an equation that isn't an exact equation, multiply through by a factor, and make it an exact equation. For us, in this course, we're not responsible for that. We won't, there are ways, I mean, the next question would be, well, how do I figure out the xy squared? There are ways of figuring out the integrating factor. We'll know of their existence, that integrating factors exist, but we won't worry about actually finding them in this class. Some other cautions. Sometimes an exact equation, like when I want to show that it's an exact equation, I'll write it in this form: some bracket dx plus some bracket dy equals 0. But it doesn't have to always be presented of that form. If I go back up here to the original equation, we could write this as divide everything by dx, and the differential equation could have been presented like this, in which case it would be a separable differential equation as well. But not all exact equations have to be of the form a bracket dx plus a bracket dy equals 0. You could take a differential equation, put it into that form, a bracket times dx plus a bracket times dy, check to see if it's exact, and then proceed through the method. Or, like in the case of this example, it's a separable equation, or it's homogeneous as well. Anyway, now you have to do some practice and then move on.